My presentation will be a review of an article done by Hafner, Meisenbach, and Sandelmeyer, and their new approach to the synthesis of boronic acid derivatives using flow chemistry. This article entails a completely new way of continuously synthesizing boronic acids on a multigram scale while diverging away from traditional batch chemistry. But firstly, what are boronic acids? Shown in the top right is the most generic structure of boronic acid. Structurally, they are trivalent organic compounds that possess one carbon boron-based bond, with the carbon being the R group in this case, and then two hydroxyl groups to fill in the remaining valences on the boron atom. Boron is a special atom in the sense that it only has 6 valence electrons and thus an unoccupied p orbital, which makes it orientated in a trigonoplanar fashion. Unlike carboxylic acid derivatives, boronic acids are not found in nature and thus an entirely synthetic class of compounds. Scheme 1 shows the synthesis of phenylboronic acid using phenylmagnesium boride, followed by trimethyl bromate, and then hydrolysis. Scheme 2 shows a very similar reaction pathway to Scheme 1, except we are now lithiating a phenyl bromide with N-butyl lithium, and then this aryl lithiate species is reacted with the same trimethyl borate, and then it is further hydrolyzed to give the phenylboronic acid. Scheme 3 shows an advance in the synthesis of phenylboronic acid, as we are now using a palladium-based catalyst to generate our species of interest. This reaction is done by reacting an aryl chloride with diboronic acid and a palladium catalyst in the presence of X-phos and the base. Listed here are some of the many applications boronic acids has achieved. I won't go into too much depth on the specifics, but it's good to know how boronic acid has changed organic chemistry. Suzuki coupling uses a boronic acid and an organohalide in the presence of the palladium complex to form a new carbon-carbon bond. This is probably the most famous example and usage of boronic acid, as it had led to great advances in the pharmaceutical industry. Traditionally, carbon-carbon bonds are just too hard to make, and so pharmaceuticals and many pharmaceutical compounds would incorporate carbon heteroatom bonds just to avoid this problem. But now with advances on the Suzuki coupling, we can now synthesize carbon-carbon bonds in the pharmaceutical industry with ease. Chan coupling reacts the boronic acid with a nitrogen or oxygen-containing compound in the presence of copper and a base such as pyridine. This forms a new carbon-nitrogen or carbon-oxygen bond depending on your starting material. Babinski and Schwarz coupling reacts a thioester with the boronic acid to produce ketones. Many boronic esters can be oxidated to an alcohol with a base and hydrogen peroxide. We have already seen hydrolysis of phenylboronic esters to phenylboronic acids in the previous slide, but further hydrolysis of phenylboronic acid with hydroxylamine allows for the formation of the corresponding phenols. From just a few examples, we can clearly see the variety of different chemical compounds that can be derived from boronic acids. Thus, this had led scientists to research further into boronic acids and new ways to access them. This article tries to synthesize a range of boronic acids using flow chemistry. So firstly, we need to understand what is flow chemistry and how is it different to batch chemistry. In flow chemistry, a chemical reaction is run in a continuously flowing stream rather than in batch production. And there are two key parameters that differ between the two. Firstly is the reaction time in batch chemistry. This is usually determined by how long your vessel is stirred under a fixed condition, whereas the residence time in flow chemistry is the amount of time the reactant spent inside the reactor. The residence time can be calculated from the volume of the reactor and the flow rate through it. Secondly, the concentration in batch chemistry is often replaced by pressure in flow chemistry. There are multiple advantages to using flow chemistry, as it allows for faster reaction, reactant optimization, improved safety, better control of the reaction, enabling reactions not possible with batch chemistry, scale up is more straightforward, cost reduction, and automation. This article adapted the halogen lithium exchange process that was seen in Scheme 2 and made an entirely new route of synthesizing boronic acid using flow chemistry. The aryl halogen starting material was mixed together with N-butyl lithium to form the aryl lithium species, which then underwent subsequent reaction with an electrophile, in this case was trimethyl borate, to form various boronic acids. It was noted in this paper that two different strategies was applied to increase the stability of the aryl lithium intermediate species. The first was to decrease the temperature to -50 to -100 degrees. This increases the half-life of the aryl lithium intermediate and allowed for extended residence times prior to the mixing of the electrophile. The second was the use of flash chemistry. Flash chemistry is when the reaction is done in less than a second. This is a direct contrast to the first strategy, as we are now focusing on the instantaneous mixing of the aryl lithium species with very short residence time. This strategy allows us to avoid the decomposition of the aryl lithium species, as it is directly quenched by an electrophile. From the article, we see that they have decided to use commercially available T-pieces in PFA tubing. This was done to simplify the setup and the handling of the entire process. The PFA material additionally allowed for flexibility and modularity. However, the downfall of these chosen equipment was that it did not allow for shorter mixing times of less than 1 second, which was needed for flash chemistry. Instead, the mixing times was optimized by adjusting the flow rate. Pre-cooling loops allow for the temperature to reach -30 degrees, as this was the lowest temperature it could reach, and this helped stabilize the aryl lithium intermediate species. The Sidos 2 syringe pumps allowed for a continuous pumping of the reagents, while the high-tech Zhang software allowed for the online monitoring of temperature, flow rate, pressure, as well as an emergency shutdown button if needed. Commercial N-butyl lithium was used as no pre-dilution was required, and the cylinder can be directly connected to the syringe pump and thus fed into the system. Aryl bromide was the halogen of choice, as this was reported that at 0.3 moles in THF, this specific reagent caused the least amount of clogging. To optimize the flow rates for these set of experiments, they kept the concentration, flow rate ratio, temperature, tubing, and T-pieces constant. The only variable they changed was the flow rate for the halogen lithium exchange. From the figure on the left-hand side, we see that a lower flow rate was in correspondence with a lower yield, and there was a significant increase in yield when the flow rate was greater than 14 milliliters per minute. Full conversion of the starting material to electron-poor rich arenes, such as 3A, was achieved when the flow rate was 24.1 milliliters per minute. Electron-rich arenes such as 3B followed a similar pattern, except these substrates react slower, so only a 77% yield was observed with these molecules. These reactions was done in a 0.1 second reactor. The figure on the right-hand side was to see if increasing the residence time of the setup could grant us better yield. And indeed, by using a 0.5 second reactor as opposed to a 0.1 second reactor, we were able to get electron-rich arenes such as 3B and 90% yield at a flow rate of 14.5 milliliters per minute. Furthermore, 95% yields could be achieved if flow rates was greater than 18 milliliters per minute. From these optimization findings, the lithiation and borylation step was to be performed using a 0.5 second reactor and a constant flow rate ratio of 4.85 to 1. This figure shows the full experimental setup for the synthesis of various boronic acid using flow chemistry and the optimization findings as discussed earlier. 3 Cerados 2 pumps were used to pump the 3 different reagents, one being the aryl bromide in the bottom left, another being the N-butyl lithium just above it, and finally an electrophile in the middle of the reaction schematic. All solutions were prepared under argon to help protect any reactive species, and temperature was chilled to -30 degrees over 24 seconds prior to mixing. Flow rate of aryl bromide was 17 milliliters per minute, whilst the flow rate of N-butyl lithium was 3.5 milliliters per minute. This was necessary to keep a constant flow rate ratio of 4.85 to 1, as discussed earlier. These two reagents were mixed using a PFA T-piece with an internal diameter of 0.5 millimeters before entering the first reactor, which has a residence time of 0.5 seconds. This reaction mixture was then placed and mixed with the electrophile, which was pumped at a flow rate of 6.12 milliliters per minute, and a second PFA T-piece, again with an internal diameter of 0.5 millimeters. This then was reacted at 0.5 residence time second. After the reaction has reached equilibrium, the outcoming mixture was directly quenched in a semi-batch reactor with 0.5 equivalents of citric acid at 0 degrees. This reaction was continuously stirred for a further 30 minutes at 0 degrees, and the crude product was analyzed using HPLC at a wavelength of 210 nanometers. This figure shows 11 different boronic acids Hafner, Meisenbach, and Senemeyer managed to synthesize using flow chemistry. Their respective yields was given as a percentage next to the molecules. Following the semi-batch quench, the organic and aqueous layers were separated and extracted twice with isopropyl acetate. The combined organic phase was dried with sodium sulfate. The solvent was removed in vacuo, and the product was then analyzed by NMR and HPLC with a wavelength of 210 nanometers to determine their purity and yield. From this finding, a lot of the boronic acid derivatives were synthesized in excellent yield with high purity of more than 95% as determined by HPLC. All boronic acids produced gave a throughput of 5.1 millimoles per minute, which is about 1 gram per minute. This would have been impossible to achieve using standard batch chemistry. Furthermore, aryl bromides containing fluorine and cyano substituents are highly likely to decompose in the presence of N-butyl lithium under conventional batch chemistry. But the use of flow chemistry has helped us avoid this problem, and the lithiation along with the borylation can be achieved in high yield, which opens up new possibilities of the range of boronic acid derivatives that can be synthesized. Another advantage of flow chemistry is the multigram scale synthesis of boronic acid that we can avoid the time-consuming step that is often needed in traditional batch chemistry. To further demonstrate the broad applicability of this new flow chemistry approach, Hafner, Meisenbach, and Senemeyer also managed to synthesize a range of alcohols and aldehydes. This was done simply by changing the trimethylborate electrophile. Once again, in all cases, this product obtained was an excellent yield and high purity. In conclusion, flow chemistry is simple to set up and easy to use. A lot of the equipment needed are commercially available at cheap prices. It can also save a lot of time as the processes can be fully automated, and even if it is not, the reaction requires little human interaction as computer software and automatic syringes can keep the reaction going continuously. Reactions can be done in a safer manner, and for this specific example, N-butyl lithium is a very dangerous reagent and it is highly flammable and can even ignite in air. But the use of flow chemistry allows it to be directly pumped into the system so that it minimizes any risk. We can now also synthesize products that normal batch chemistry cannot in good yield or high purity. As seen above, all reactions gave products an excellent yield and high purity, and this was done simply by adjusting and optimizing flow rates. Good throughput of products was achieved at a scale of 1 gram per minute, which was nearly impossible to achieve in traditional batch chemistry. With further advances in flow chemistry and the scale-up process, we can have an even greater impact of how chemistry is done, and we might also be able to change the way the pharmaceutical world industry completely. Thank you.